In this video I would like to talk about the field strength, in particular of course of the gravitational field, but the importance of this value becomes clearer when we for example look at other fields like the electric and magnetic field. So at the current stage, what we know about the field strength is the force, the gravitational force is m times g. And the interpretation that we had so far was always because each force is m times a, the acceleration. We could conclude that a is equal to g. So g is something like the acceleration on the Earth's surface. That worked very well in a homogeneous field model that we have been using in the past. So, as you can see here, and the homogeneous field, that the lines that represent the field vectors or the force are parallel to each other. However, we have to keep in mind that in this model, well, that's what we've done before, we should draw arrows like this because they represent the force, and if a mass is here, then the lowest vector shows the force, gravitational force acting on that mass. And for this one here and for that one there, we see that the length of the arrows, so the magnitude of the force, is always the same. However, when we combine these arrows to one long arrow, this information gets lost. So just by looking at this homogeneous field or the picture of it, we couldn't tell that the force is constant and independent from the distance between the mass and the surface here. So what is new now, and that's what we've learned in the radial symmetrical field or radial field. We have the field vectors still perpendicular to the surface. However, since we know that the Earth is a sphere, at the end we get a different picture. Still, we have to keep that's what we have been observing. When the distance between the Earth's surface and some mass increases, that the force that is acting on that mass becomes smaller. So indeed it was more like this. And again, when we look at that one here, we don't see, because the arrows have all the same length, and so we only have the direction of a force at a certain point here in this field. And that's where a new interpretation of this mass, of this field strength or the value of G comes into place. So let's have a look at the formula that describes the gravitational force here. It is the capital G times a small mass times a big mass, r squared. So usually, or in many cases, we use one large mass that builds up this field that we look at, and a smaller mass that is being put into this field. And then we want to find out more about the interaction of the two masses, and that is a force, an attracting force. So when we look at this, we want to find out, or we want to know how the force depends on the distance between the two bodies. And that becomes clear by looking at the formula, of course, because as we can see here, when the radius is increasing, the force must decrease. However, this is not clear from this stage when we look at just the picture of the field lines. So now we look at a new interpretation of this small g, and I'm gonna draw something. What we can see in this picture here is, if we put a little surface parallel to the ground, or the so like something like a piece of paper, okay, parallel to the surface here of the Earth, then we can count the number of field vectors that pass through that area or that phase. And in the homogeneous field, it doesn't make a difference if we go a bit to the left side, a bit downwards or upwards. The number of field lines, or the so-called density of the field lines, remains constant in every on every location. But this is different when we look on the right side here, and I'm going to enlarge that a little bit. So you have the same like piece of paper here, needs to be a bit bent because the surface is bent. But if we move that a bit away from, or we increase the distance, then we see that the number of field lines becomes less. That means the density of the field lines changes with its distance from the center of mass. And this is an indicator for the fact that the force is becoming smaller when the distance increases. So we need another value, basically. It's called the field strength, that gives us information about the strength of the field at a certain location. Or let me put it in a different way. How big is the force at any point in this field? Well, we've got the formula here where we can calculate it, but in the formula we have the g, which is a universal constant. We have a radius which is a kind of independent variable, and we have the capital M, which is, in this case, let's say it's the Earth's mass, and then we've got the small m. Because we need, in order to have a gravitational force or interaction, we need to have two masses. And this could be the small m. So then we've got everything we need in our formula to calculate the attracting gravitational force. But the question is, if we remove that mass, yeah, that was nice. Do we have to remove the vectors as well? So what happens to the field, the gravitational field of the Earth, if there is no other mass in this field? Does it disappear or does it still exist? The question is a bit tricky because, to be honest, the field doesn't exist at all. Never. Because it's just a mathematical model. But we said that the gravitation is caused by a mass, and it couldn't be, or would be strange if we had like a mass is somewhere here. Okay, so there should be, and we know that the field lines, its length is infinite, so it never ends, and somewhere there must be a mass. But what about a field on this side, if there is a mass on the other side? Yeah, so it's not consistent if we say the field only exists when there is at least one other mass around the Earth. So the field should still be there without any other mass, because it has nothing to do with another mass. It's the field, the gravitational field of the Earth, and not of the other mass. To be exact, another mass has its own little gravitational field. But this is so small compared to the one of the Earth that we can just ignore it. But to come back to our main problem, we need a value that describes the field without this other small mass that interacts with this field. And what we can do in that case, we want to make the force independent of that small mass. So what we do is we divide it. And we end up with G is equal to m by r squared. And if we look on this side here, what happens if we do that? F divided by m, then we've got this G. So that's what we do here. And that is called the field strength. And that gives us an idea that describes the field's vectors in order of the mass, the position, which is indicated by the radius, and the universal constant. So we can reconstruct the gravitational field of a mass just by these two information, nothing else. So we don't need the smaller mass. But if we have the field strength at a certain place, what else does it tell us? if we assume that the mass will be 1 kilogram, that means the small m would be 1. Or in that case, if we just multiply 1, it doesn't change here, the value, okay? So in case that we have a small mass of 1 kilogram, the value for G and for F would be the same. Yeah, if M equals 1 kilogram. So the field strength, the G, tells us how large the force that acts on a mass with a of 1 kilogram on that position in the field that we are looking at. So now we have 3 different interpretations or concepts of the field strength. So first one that was here, that was the acceleration. So if we multiply or if we just let we drop some object in the gravitational field, then the G is equal to A, and that's the acceleration. Of course, we have to keep in mind that the attracting force is acting in both ways. So also the mass or the Earth is attracted by this 1 kilogram somewhere in its orbit, and they are equal. Both forces need to be equal. That's what we know from Newton's laws. But if we stay with our very simple model that we say, okay, m times g, or m, that's not even a simple model, but both forces are the same. So mass of the Earth times acceleration of the Earth is equal to this 1 kilogram times this acceleration here. Now, if we say that this is 1 and this is, for example, 10, yeah, because we know that G is 10. Now we know that the mass of the Earth is 10 to the power of 24. So that means that the acceleration would be 10 to the power of minus 23. And this is so small that the Earth is not really accelerating. It also, as I've said before, there are, on the opposite side of the Earth in physics, we like to say that in Australia, for example, there's also a physics teacher that makes the same experiment with a mass falling down on the floor. So there is also a force here acting on the Earth. Yeah. So it's really you wouldn't notice that. But if we look at the moon, for example, the moon is quite heavy, and we know that the tides in the ocean, for example, are caused by the moon's mass, and the moon is really pulling on the Earth. And well, that is something that you would learn at university, but so the center of the Earth and the center of the rotation is not the same, and this is due to the mass of the moon, and both of them orbit around a common center, and that's the center of mass of both bodies, okay? So that is somewhere here. And so the rotation of the Earth is not so straightforward as we always assume. So one last thing in this video, if we calculate with the gravitational force, and we want to find out more about circular orbits around the Earth, like the ISS that we've had before, we need to be sure that the total distance, the r, is always from the center of mass of the ISS to the center of mass of the Earth. Well, the ISS compared to the Earth is not very big. So if we say, for example, this is 408 kilometers, and this is something that's around that, then we don't have to see how big the ISS is, if it's like 20 meters or 30 meters. That won't change our result in a significant way. But the radius that we insert here is always the sum of the altitude plus the radius of the Earth.